So good morning, everyone, and welcome to the first edition of International Conference of Engineering. Why milliseconds matter? Or what do you think? Do they even actually matter? Let me answer it. According to a study done in 2017, Amazon found that every 100 milliseconds of latency in their APIs used to cost them approximately 1% of their sales. Google found that extra half a millisecond in their search page generation time dropped their traffic by 20%. A broker could easily lose up to $4 million in revenue if their electronic trading platforms are just 5 milliseconds behind their competition. So sometimes making things more efficient is just a matter of milliseconds. Now let's put this thing into the perspective of our REST APIs. Now, most of us know what REST is, and I'm not going into the nitty-gritties of REST, but let me show you a small performance review of REST with gRPC. We did a POC to evaluate how gRPC stacks up against REST, and we were pretty amazed to see the results. We created a service for both gRPC and REST, and to test the actual performance, we sent 1,000 requests for each user, and we tried simulating 100 concurrent users load at the same time. Now, this is what the results look like. The CPU utilization was drastically reduced from 85% in case of REST to an approx 50% in case of a gRPC unary operation. The API response time came down from 6.8 seconds in case of REST to a 3.3 seconds in case of a gRPC unary operation, while to a staggering 1.1 second in case of a gRPC streaming operation. Similarly, requests per second was very high in case of gRPC as compared to REST. Now, these may change depending upon use case to use cases, but they give us a fair understanding about where REST stands against gRPC when it comes to performance. So aren't we saving a lot of time and resources when we talk about gRPC communication? So that's a talk for the day. Why milliseconds matter and how we can actually move from REST to gRPC. Now, before we dive in, my name is Abhishek Bansal, and I work as a mobile architect for McDonald's. I am accompanied by my colleague Gaurav Mehta, who is a senior lead again for McDonald's. And both of us have been with Sapien for 3 years now. And we hope by the time the session ends, you should be able to leverage gRPC in your own existing ecosystem. Just quickly going through the agenda, we'll be talking about RPC and gRPC and what exactly makes gRPC different, what all frameworks it leverages, and then a quick demo of what we have prepared for you, and then finally the gRPC adoption practices. So in 1994, Waldo said every 10 years, a furious bout of language and protocol design takes place, and a new distributed computer paradigm is announced that is compliant with the latest programming model. And it is pretty accurate if you look back in time. This is what REST did to SOAP, and probably now REST is at the same crossroads. Now, REST is definitely great. I have been using it for a long time, but REST has its own set of limitations. And that's where RPCs come into picture. Now, what exactly is an RPC? RPC is just a client-server communication that uses a function call rather than a usual HTTP call. For an RPC, for a HTTP, your resource is a fundamental unit, but for an RPC, the function is a fundamental unit. While now RPCs have been there for a very long time, it's not something which is a new concept. You guys might have heard of Corba, RMI, distributed COM, etc. And all of them leverage RPCs. RPCs, they provide a well-defined interface and type safety, and it uses an interface definition language as a form of contract on functions to be called. So that was about RPCs. Now, what exactly is gRPC? Now, gRPC is more of a high-performance communication technology that evolves over the age-old remote procedure calls. Now, remote procedure calls have been there for a very long time, probably 2 to 3 decades, while gRPC was something which originated in 2015 by Google, and it was based on one of their internal projects called Stubby. Uh, Although it was internal to Google, but nowadays Stubby has been rebranded as gRPC, and it's a free open source project with the open specifications and roadmap. It's also part of the Cloud Native Computing Foundation. Now, also gRPC, in gRPC, the G does not stand for Google. It's actually a reverse acronym which stands for gRPC Remote Procedure Calls. So on a high level, gRPC is equal to HTTP2 and protocol buffers. Now, gRPC, it ties itself to HTTP2, and 2 being more specific over here and not 1.1, which is used in REST, because gRPC leverages a lot of streaming capabilities of HTTP2 for its functionalities on the transport. On the schema side, it leverages protocol buffers or protobuf, just the way we have a WSDL for a SOAP API or a RAML for a REST API. Now, to understand how the flow of information works in case of gRPC, let's say you have a Java service. Now, you generate the gRPC service using the service definition. Now, this gRPC service simplifies the server-side logic by providing the low-level communication abstractions. Now, then you might have clients such as a desktop or a mobile, and they might be talking to the Java service using the stubs. Your Java service might internally be talking to a Python service, again through stubs with gRPC generated. And your Python service might be again talking to a C++ or a Golang or a Ruby service, again through stubs. Now, the beauty of this model is that uh, all of the communication abstractions, all of the communication which is happening between the client and the server and the microservices is done through the stubs that gRPC handles. And additionally, in case if you have different teams working on different modules in different languages, such as Python or C++, it's not a problem. All they have to agree is to a service definition contract. So gRPC definitely is more of a polyglot. Now, to understand more about HTTP2 and the protocol buffers, I'll hand it over to Gaurav, who can quickly give us a walkthrough about them and show us the way how it works.
Thank you, Abhishek. To understand how gRPC saves some extra milliseconds for us, let's go one step deeper to understand how HTTP. Let's go one step deeper to understand some internals. HTTP has been there for more than 3 decades with us. It serves us well, but still there are some problems, like limited parallelism, where every HTTP connection needs its own dedicated TCP connection. They cannot be reused. Header line blocking problem with pipelining. In HTTP 1.1, there was a new concept came which called pipelining, where the client send a number of requests simultaneously to the server without waiting for the response. Uh, what happened in the latency-prone network? Some requests can go out of order, or they require retransmission, and all the training requests got blocked, which hamper the overall communication significantly. The header portion of all the requests are mostly redundant. We need to send the headers in all the APIs. They cannot leverage compression, and sometimes header size is even larger than the body size. This is all very inefficient. So most of this problem got resolved with HTTP 2.0, where the multiplexing can be supported. With gRPC, as multiplexing is now supported, we gRPC is offering 4 kind of communication mode to us: unary, server streaming, client streaming, and bidirectional streaming. We will take in more detail in our upcoming demo. So HTTP 2.0 makes the header and body section converted into frames, which makes headers can also leverage compression. There was a protocol called XStack, which was introduced in HTTP 2, which take care of header part so that we don't need to transmit it every time. So it checks the subsequent APIs and see if the header section is same, then it omits the header from the request. Now TCP connection can also be shareable between multiple API requests. This can be a breakthrough for low-end devices, for example, mobile devices or IoT devices, where making and breaking of TCP connection consumes a considerable amount of CPU utilization, and eventually it drains the battery. Okay, so here I have an example where we are downloading two images, one with the HTTP 1.1, and the same image being downloaded through HTTP 2.0, and you can see there's a very good amount of difference in the total download time. Okay, so what do you think of what is the native language of computers? Is it JSON? No, right? Binary is their native language. Binary is the one where they are most comfortable with. Better compression, low CPU utilization, uh, low memory footprint, and many more. There has to be a protocol which is binary based for most of the communication in the network. And yeah, protocol buffers is the answer. Protocol buffer is a binary based serialization protocol which is platform agnostic. So this graph shows when we send the same amount of data through JSON versus protocol buffers, and what is the like total number of total number of bytes being transferred through wires. So you can see there is a astonishing 30% less data is being transferred through protocol buffers. Protocol buffers are efficient, they are machine readable, there are a number of compilers available for them, and most importantly, they are type safe. So let's take a look at an example protocol buffer file. We need to create a text file and save it with .proto extension to create any protocol buffer. So we have like two sections in every regular protocol buffer file. One is the message section, which looks like any other entity in the system. It's a product, for example, here where I have multiple attributes. There are most of the data types are supported, like int, string, double head, etc. Uh, we need to assign a unique integer to all of the variables here. These integers are being used by the underlying serialization protocol, and it has to be unique within the same message block. And we can have like multiple messages in the same file. Uh, the second section is the service section where we define all our RPC calls. Uh, in every line item, you can see like it looks like any other protocol, any other function declaration where we have a function name, uh, we have a request type and the response type. We can also use stream keyword to define which part of the communication is streamable, either client side streamable or the server side streamable. And yeah, now we can even add our comments as well in the same file, like JSON. So protocol buffer has its own compiler called proto-C, which we can use to compile our protocol buffer file to any of the language stub. For example, here we are converting this product.proto file into Python code. Protocol buffers are like supporting majorly three languages out of the box, like C, Java, and Go, and all other modern languages are provided their C style wrappers, which got converted into C language. Okay, so time to see the code, how we can uh, implement them in our live project. So for demo, I have created two apps. One is the server side and the other is the client side. The server side I have written in Java, and client side is actually an Android application. For Android application, I use Kotlin because in back 2020, Google launches gRPC for Kotlin. So let me show you the app first. So this is my app where I have two options, unary and binary communication. When I open unary communication, I have a set of products with some of their attributes. I can do a filter on it based on various categories. And similarly, I have bi-directional streaming option where the similar products are there, but now this time the request is streamable, and I'm using the same connection to get the product. And all these products are actually coming through a paginated stream where the client is requesting new page every time, and I'm not closing the connection as soon as user is there on the screen. So when I go back, then I'm closing the stream. So let's see the server side first. To set up grpc, we need to include a number of dependencies in our gradle file. So I'm using this gradle based system. And the most importantly, I'm using we need to include this protocol buffer compiler, uh, so that it can compile our protocol buffer files. And similar dependencies we need to keep at the client side as well. There also we need to keep a dependency for uh, uh, Kotlin and the similar protocol buffer compiler protobuf we need to keep. So here I'm keeping the same protocol buffer file which we just discussed in our deck. So there are a number of RPC calls which I have defined. I will cover these two RPCs where a unary communication and a bidirectional communication. So let's start. So as soon as I build my project for the very first time, the plugins which we define in our Gradle file generate a few Gradle tasks for me. So this one is important. Gradle task generate proto. When I run this task, it will generate a number of stub code for me, number of classes for me. For example, I am using this product catalog service. You can see there's a product catalog service simple base. This is being generated. I need to inherit this class and give the implementation of all my RPC. So this is my class where I'm inheriting, and there are like all the RPC function which I need to define here. Let's take the look of unary RPC first. This is called filter product by category. So there are two parameters here, product list request and the stream observer. So this request is being transferred from the client side. So to see how we send that request, let's see the client as well. So here, actually there are like three steps process for the client. We first need to create a channel. Then we need to create a stub object. So there are two options. Either we can use a blocking stub or a future stub. So as name suggests, blocking stub will be blocking, and future stub will return a feature to watch on the response. So and the third step is like create a request object and then call the main RPC function. This is my RPC function. So you can see like the same name, filter product by category, and this request object. So as soon as I call this RPC function, the request will come to my server side here, the filter product by category at the server end. Here I'm using MongoDB to get the data from a database. I have this product of class, and I will create the response object, and I will call this on next function on my stream observer with the response. And then I am calling this on complete function. It will close my stream. So as soon as I call this on next and on complete, I will get this particular blocking request will be resolved. So it will be a blocking call. We should call it in our worker set, and it will got resolved, and we will have the response. So this way of communication really look like any reactive programming constructs where we have a number of subscribers and a publisher, and we can publish on stream. All the subscribers get notified. So this is how Unity is working. Let's quickly take a look at bidirectional example as well. Where so the function is a little bit different here. We don't have the request here. We have a stream observer as a request and stream observer as a response. So the server has to create a stream observer object and implement a few number of methods like on next, on error, and on complete. And this object will be transferred to my client side. So in client side, I have bidirectional class as well, where I'm doing the similar things like the unary example. The one difference is now this time I'm creating a new step, not a blocking step, because new step I need object of stream. So this is my RPC call, get product list. So this will return the same object which my server has created here, this object stream observer, and I need to call the on next function every time on this stream whenever I need next set of data. So I'm calling it here, and in my so when user reach at the end, this function will get called paginations call listener. There I am calling with the next page number. So every time I call this on next, I will get a callback here in the server side on next function. So I can read this request, get the page number and the product type, and prepare my response using same DAO, and then call the on next function to send the response. So the client and the server side, anybody can close the stream anytime by calling this on complete. I'm closing the on complete here at the server side, where whenever I consume all the data from my database, and I can also send a specific errors to my client calling this on error function. I'm not calling here, but we can still call it. So this is how client and server both are communicating in a dialogue kind of fashion, right? That's all about demo. Let's go back to Abhishek to see how we can adopt this system in our live project. Back to you, Abhishek.
Thanks, Gaurav. So wait, will I have to rewrite all my APIs again? Well, the answer is no. We don't intend to say that gRPC is the replacement for REST. Instead, with the current reach of REST, that's hardly a possibility. In fact, both REST and gRPC will have to coexist. So how do I ensure that? How do I integrate gRPC with my existing ecosystem? Well, gRPC Gateway project comes to the rescue. A gRPC gateway allows us to design gRPC and HTTP JSON services at the same time. It uses a custom protocol buffer generator to that generates a simple reverse proxy, and it translates on the fly from JSON to protocol buffers and back again. Now, for example, if you look over here, the gRPC gateway generates the gRPC service and also generates a reverse proxy. And now once you start the reverse proxy, it serves a HTTP REST interface. And in the background, it translates your JSON request to protocol buffers and sends it to the gRPC service. And then the translator is, and then it's translated on the back, on its way back. Now, gRPC Gateway also provides us a Swagger and an open API generator, and has been widely accepted by the gRPC community. The gRPC Gateway allows you to define the URL path and the HTTP to gRPC service method mapping with a simple annotation scheme in the protocol files. For example, in this given proto file, which you have shown in the demo, we added the HTTP JSON annotations to these previously defined services, and you can see that HTTP GET, POST, etc., and the URL path mappings are defined within the RPC definitions. So that's how it's working under the hood. So what are some of the key takeaways from this session? Primarily, gRPC is more about HTTP2 and protocol buffers, and gRPC is not going to act as a replacement for REST. We talked about a lot of good stuff about gRPC, but there are definitely some challenges. It's because gRPC is still something which is evolving, and it has its own share of challenges. For example, limited browser support. Now, it's difficult to directly call a gRPC service from a web browser today. I'm not saying impossible, but it's difficult. gRPC heavily uses HTTP2 features, and the kind of control required over web request, it's difficult in case of a browser. Although we have a tool called gRPC Web today, but it is something which is still evolving, and both Google and a company named Improbable are working on it. It's not human readable. Now, HTTP requests are usually verbose in nature. With every advantage, you get a trade-off also. While protocol buffers are binary encoded, they are fast and efficient, but they are not human readable. So it makes them a bit difficult to debug. And then lack of developer tooling. While we have used multiple tools in HTTP 1.1, and there are a number of tools available for at our disposal, but moving to HTTP 2 and protocol buffers, it requires a new set of tools. So the popularity of gRPC has grown drastically over these years, and there are many large-scale corporations like Netflix, Docker, Cisco, CoreOS, Square, Lyft. They all adopting gRPC, but it is still early days for gRPC, and there are some definite teething troubles, but the future still looks bright. With this, I'll wrap up the session, and we are open to any questions. Thank you.
Thanks a lot, Abhishek. Gaurav. I see a couple of questions on the Q&A box, and I'm just throwing them up to you. How to authenticate an SSO application with gRPC or HTTPS from a Python API?
Gaurav, will you take that up?
Yeah, so gRPC came up with many type of authentication like Auth 2.0 is supported, and Google ID token is also supported. So they all we can utilize while creating the channel object. Similarly on the server side, so they are supported. Most Google technologies are widely acceptable with. I hope that answer your question.
Can you talk about Akka with gRPC integration? What if there are good features like throughput latency and any insight between GraphQL versus gRPC in a mobile domain?
Okay. So see, GraphQL is more GraphQL also leverages RPCs, and it's more GraphQL is more about remote data access and RPCs combining. Uh, Both GraphQL and gRPC actually are advantages when it comes to performance as compared to the usual REST API calls. Although we haven't specifically tested out GraphQL with gRPC, our focus was more towards the REST part, but they both stack up pretty well as compared to REST as far as performance is concerned.
Okay, there are two questions. I'm combining them, Abhishek. Does the gRPC interact well with the Auth 2.0 mechanism and Spring Boot? And what Auth 2.0 mechanism does gRPC support?
Uh, I don't see like it can really replace altogether, but uh, there are a few examples which gRPC community has put in, but it's still evolving. I don't see like it will be replacing.
And what's the readiness for gRPC for HTTP3?
Oh, that's a good question, but we haven't.
That's a good question. I don't think even it is still evolving for
So
HTTP2, but
yeah.
uh, I don't see any roadmaps as of now on their GitHub page or in the community for HTTP3. There could be, but
And I'll just take one last one for both of you. How about an application with SSO integrated in DEX from an organization side and the application deployed in Kubernetes in GCP?
Vishal, I think I would have to get back to the respective person. I don't have any
Sure.
immediate answer as of now.
Sure. And these questions are here, Abhishek, Gaurav. Thank you so much for a wonderful, insightful session.
Thanks, Vishal. Thank you,
thanks,
everyone.
Vishal.